situation where we're dealing with the Pythagorean theorem, so it's x squared plus y squared equals, and I'm gonna call it L squared. I'm gonna call this side x. Picture it as if it were in a coordinate plane. This would be your x-axis, this would be your y-axis. So at this point right here, our ladder's 13 feet. We're going to be 5 feet from the wall, and we're moving at a rate of 5/2 feet per second. So from that, we're going to take the derivative of this. So we get 2x dx dt plus 2y dy dt equals 2l, and then it's dl dt. Again, our denominator is second, so everything is with respect to second, so it's with respect to time. That's the reason we have the dt in the denominator. T is not a variable in the problem, but it is a variable when we do the related rates with it. At this point, the 2's in common everywhere, so I'm just going to take that out. So I have x dx dt plus y dy dt equals L dl dt. All right. Now, at this point, we're going to plug in specifics for this problem. X that we're concerned about is 5 feet. The dx dt is 5/2. Your y value, we don't know right now. Dy dt is what we're looking for. And our L is 13. Now, based on that, we're missing two things. We're missing y and we're missing dl dt. Now, how do you think we could solve for either one of those?
Could you do y with Pythagorean theorem?
We find y with the Pythagorean theorem. So we have 5 squared plus y squared equals 13 squared. So it's 169 minus 25. So y would equal to square root of 144, which would be, as you have said, 12. All right, now, your dl dt, what does it represent in this problem? What does dx dt represent? Yeah, the change of this length, right? This length is changing at 5/2 feet per second. So what is dl dt going to represent?
Constant.
It's going to be constant here, yeah, because your ladder's rate is not changing. As it slides down the wall, it's rigid. It's going to stay at 13 feet. So what is the rate of change in its length? It's 0. So we end up with a 0 on that side. So 0 equals to 25/2 plus 12 dy dt. So 12 dy dt is equal to 25 over 2. It's going to be negative. So now divide everything out by 12. So we get that dy dt is equal to negative 25 over 24. Now, the units. Everything in here is in terms of feet, right? And the changes are in terms of seconds, so it's feet per second. Now, we got a negative answer here. Does that make sense? Or was I wrong? Did I make a mistake somewhere?
I think it makes sense because the distance is decreasing.
Yes, the distance, the height that the ladder is up the wall is decreasing. So we should get a number that is less than 0. Okay, are we good here? Now, there are a couple of other things that we can talk about in as far as the ladder's problem is concerned. We can also take this exact scenario here and talk about the area that's formed in here. And consider at what rate is that area of the triangle changing. Well, what is area for a triangle?
Length times width divided by 2.
But for length and width, I'm going to put x and y because that's just how I've got them labeled in this problem. So area is going to equal to 1/2 xy. Now, when we take this derivative in this problem, we're going to need to use the product rule. So, what am I going to get on the left-hand side? This is not the tough question.
dA over. Or 0.
Yeah, dA dt.
Okay, yeah.
That's dA dt. No, it can't be 0 because the rate is changing there. The area of that triangle is changing, so it would not be 0. All right, now, we're just taking the derivative. So how would we do the derivative of 1/2 xy? And there are a couple different ways to think about it.
Is it the chain rule?
Wouldn't be chain. In this case, it would be product. Yeah. So let's take the first term and call it 1/2 x, and let's take the second term and call it y. So it's going to be the first term times the derivative of the second term. And what would be the derivative of
dy dt.
dy dt? And then the derivative of the first term, which is what? 1/2
dx dt.
dx dt, yeah. We have to take the derivative of x with respect to time. So it's 1/2 dx dt times y. And again, we're not taking the derivative of the y portion, so we don't put the dy dt with it. All right, so let's start plugging in what we know. dA dt is what we're looking for, correct? Okay. Now we get 1/2. All right, what is x here? 5. And what is dy dt? Yeah, that's what we saw for in the first part, right? So we get negative 25/24 here. All right. dx dt is 5 over 2. Yeah, just 5 over 2. 5 over 2. And then your y is 12. Okay. So, we get negative 125 over 48 plus 60 over 4. And we need a common denominator, right?
48.
Huh?
48 could be because you multiply 60 and 4 by 12.
Yeah, multiply this by 12 over 12. 720, right?
Yeah.
And then 720 minus 125.
595.
Over 48. And that's going to be areas in terms of what?
Feet squared.
So it would be square feet per second. So that area is changing pretty fast, and it's actually increasing at that point in time. Because if you think about it, when it's up against the wall, the area would be 0, right?
Yes.
So as it starts spreading out at the beginning, the area is going to get a little bit bigger, right? It's going to be growing. When it gets past a certain point, though, then it starts getting closer and closer to 0 again. Where do you think that point is?
Like on a unit circle or like just a point?
If you use the unit circle, that's fine. Where?
X and Y are equal.
Hmm?
After X and Y are equal.
So it'd be a 45, 45, 90, right? Yeah. At the point where X and Y is equal, you have a isosceles right triangle. That's when
Area
The-
enhancement.
area would go from increasing to decreasing. Y'all good with that? Okay. Now, one other question that we can ask about a ladder problem. There's also a change in the angle here. If I call that angle right there angle theta, there's a change in that angle. So my next question is, part C, at what rate is the angle between the ladder and the ground changing? Well, at this point right here, I'm going to need to go with trigonometry. Y'all are welcome. So, in dealing with this and dealing with trigonometry and this, we can use sine, cosine, or tangent, any one of those. But it's beneficial in these problems to make sure one of the sides you use is one that's constant. Because the constant side is going to have a derivative of, starts with a Z and sounds like zero.
0.
0, yeah. The constant side is going to have a derivative of 0. So I'm going to want to make sure that I use the hypotenuse. So I'm either going to go sine or cosine here. Now the second thing is, you also would like, sometimes it's more difficult to do it like this, but you often try to get the denominator to be the constant term. Now, before I go any further with this, I want to go back to this. In this problem right here, if I had plugged in 13, if I had said x squared plus y squared equaled 13 squared, I would have ended up with the same results, because that derivative of that constant would be 0. Everything on the left-hand side of the equal would carry on as it did before. But if I have a constant throughout a problem, I can go ahead and plug in that constant, take its derivative, and get 0. Makes the arithmetic a good bit easier. And if that term is the denominator, it makes it even easier. So, now, you can't, I'm asking about 5 feet right here. Well, I can't plug in 5, or I can't plug in 12 here because those sides are always changing. So there is a change related to that. So if you plug in a constant, just be careful and make sure that it's something that is constant throughout the entire problem. So let's go with this. Can I erase this arithmetic over here?
Yes, sir.
All right. Now, sine or cosine, which one? Sine, okay. So I'm going to say that the sine of theta is equal to, and I'm going to list it as it is in this problem, y over L. But again, what did we say that L was? 13, and it's 13 constantly throughout the problem. Right? Okay. So, 13 times the sine of theta is equal to y. Again, have not done any calculus to this point. Everything right there is just trigonometry and me writing it. All right, so let's go ahead and differentiate this one with respect to time. So the derivative of 13 sine theta would be 13 cosine theta d theta dt. Are y'all good with that? Okay. And then what is the derivative of this right-hand side? dy dt. Okay. So let's fill it out. Now we've taken the derivative. Now we can plug in the specifics for this situation. So I've got 13 times. Now, what is the cosine of theta at this point when this is 5?
5 over 13.
It's 5 over 13, yes. And again, d theta dt is what we are looking for. And dy dt is what?
Negative 25.
Yeah, it's still negative 25 over 24, right? Okay. Okay, so my 13's going to play with the dodo bird. So I've got d theta dt equals negative 25 over 5 times 24. So I get negative 5 over 24. And I'm going to say that this is per second. Now, what per second is it?
Pi.
It's actually not going to be degrees here. It's going to be radians.
Yes.
So, I knew what you were saying. It's going to be radians here. Now, technically, there are not units with radians. I'm going to put radians per second here, but technically, a radian is not really a unit, because what a radian is the measure, it's the ratio of the arc length of a circle to its radius. Whatever that ratio is how many radians that angle is. Now, if you think about this, if this is in terms of meters and this is in terms of meters, meters would cancel out, right? So you just have whatever that ratio number is. Now, a lot of people aren't comfortable with just saying negative 5/24 per second, so they like putting radians per second in, but either notation is fine. You can say negative 5/24 per second or negative 5/24 radians per second. Either one works out fine.